We do need to know these exponent rules to be able to do today's lesson, but I'm going to give you a shortcut, maybe an acronym that you may have seen before. So for the product, quotient, and power property of exponents, you may have learned this acronym MADSPAM. That stands for if you're multiplying the bases, you add the exponents. If you are dividing the bases, you subtract the exponents. And if you have a power raised to a power, you multiply the exponents. Have y'all seen that acronym before? Yes. MADSPAM. Multiply, add, divide, subtract, power to a power, multiply. Obviously, we have the two other exponent rules. I mainly need us to know these MADSPAM rules today, because what we're actually learning for today's lesson in 4.3 is the properties of logarithms. But since exponents and logarithms are inverses, they're the same properties. So if we look at today's notes, we have all of the properties of logarithms. But if you look at it closely, we still have MADSPAM. Multiply, add, divide, subtract, power to a power, multiply comes right here. If you are adding logarithms, you can condense them by multiplying the arguments. If you are dividing the logarithms, the argument, you can subtract the logarithms. If you have a logarithm with a power and the argument, you can move that to the front as a coefficient and multiply it. So we are still doing the MADSPAM rules in both directions to either expand or condense logarithms today. This fourth and final logarithm property is called the change of base property. We will use the change of base property at the very end of today's notes, but we're really focusing on these MADSPAM rules. Multiply, add, divide, subtract, power to a power, multiply. That is the product, quotient, and power rule for logarithms. The same way it's the rules for exponents. So what we're going to be mainly working on today is expanding and condensing logarithms. Let's say perhaps we have log base 4 of 7 times 5. It's very clear to me that we are multiplying these things inside the logarithm, which means if I'm expanding them into multiple logarithms, what will I do with the two logarithms? If I'm multiplying, I will add. So we would expand this by writing log base 4 of 7 plus log base 4 of 5. We've expanded it using the properties of logarithms. If we look at the second example here, log of 10x, this is implicitly multiplication because we know two things that are stuck next to each other are multiplied. So again, how do we separate these if they are multiplied as an argument? We will add them. So this is log of 10 plus log of x. Now, when there is only numbers, meaning the base is a number. By the way, what's the base here? Not e, that's the natural log one. 10, this is the common logarithm, nice. If there's only bases showing, like there is in this term right here, we're going to want to do the log loop to try to simplify this. Remember, this is log base 10 of 10. Is anybody's spidey senses going off on what log base 10 of 10 is? Yeah, this like essentially becomes 1. So really the final answer here should be 1 plus log of x. If we can simplify it because it's only numbers and those numbers are a part of the same power family, we're going to need to take that shortcut and simplify it. All right, that's the multiplication. That's the product property. Now if we have the division property or the quotient property, clearly we can see these are divided. What does dividing on the argument mean I'm going to do when I separate these logarithms? Subtract. So this is log base 7 of 19 minus log base 7 of x. I see that right here we only have numbers, so we have to think for a second. Are 7 and 19 a part of the same power family? No, because 7 times 7 is already 49, so there's no way. So we're actually done. We go to the next problem. Again, I clearly see there's division, so I'm going to take care of that division bar first. This is going to be the natural log of e to the third power minus the natural log of 7. Ooh, but what is the base of a natural log? E. So this right here is like saying log base e of e to the third power. What happens to the log base e of e? They cancel out, so this just becomes 3. That's the quotient property. If we look individually at the power property or the power rule, if we notice that the argument has an exponent, that's a power to a power or a logarithm to a power, we're going to move it to the front and we're going to multiply it as if it is a coefficient. It goes in front of the exact logarithm it's a part of. So this becomes 4 times log base 5 of 7. So we look at the second example. Let's see if we remember this from last class. If we have a square root of x and we want to represent that as a fractional power, how would we rewrite that? X to what power? 1/2. Yes, the square root is a 1/2 power. We're going to want to represent any of our radicals as a fractional power, especially when we're trying to expand these logarithms. Because if we see, now we have an exponent, and where does the property tell me I can move that exponent? The front, so boom. And we have 1/2 times the natural logarithm of x. Now that's taking each of the properties a single time. What if we start making it more complicated and we have more than one property happening at the same time? We're going to deal with the properties as simply as possible. Right here, log of x times y over z. There are 3 letters, x, y, and z, yes? When we separate this argument, we're going to separate it into 3 separate logarithms, one with x, one with y, one with z. Anything that's coming from the numerator is a positive logarithm. Anything coming from the denominator is a negative logarithm, which means when we expand this, it would become log of x plus log of y minus log of z. Bonus question again, what is the base of this logarithm? 10. Nice. If we look at the second example here, there are only 2 letters. So when we separate this, how many logarithms should I see? 2. Nice. Okay, we're going to separate it with the product rule and the quotient rule first, then we'll deal with the power rule. If we separate this, this is going to be log base b of x squared plus log base b of y to the 1/2. Ooh, where'd that 1/2 come from? The square root can be represented as 1/2 power. Now that we've taken care of this product rule and quotient rule, now we can deal with the fact that there are still exponents inside these logarithms. And where can those go? The front of its term. So we're going to take those powers and move them directly to the front of its term. This becomes 2 times log base b of x plus 1/2 times log base b of y. Questions, comments, concerns? What if there happens to be 2 things in the denominator? And you might be thinking to yourself, Ms. Quigley, there's not 2 things in the denominator. There's a 36y to the 4th power. 36 is separated from y to the 4th power because they are technically multiplied right now. So we actually have 3 pieces in the argument of this logarithm. We have the cube root of x, we have the 36, and we have the y to the 4th power. If there are 3 separate things in my arguments, how many logarithms should I see at the end? 3. Nice. So if we separate it, anything from the numerator is a positive logarithm, anything from the denominator is a negative logarithm. I'm going to write this as log base 6 of x to the 1/3. Where'd the 1/3 come from? Cube root. So a square root is 1/2 power, a cube root is 1/3 power. Then I'm going to subtract log base 6 of 36, and I'm going to subtract log base 6 of y to the 4th power. Since both of those terms came from the denominator, both of those logarithms are negative. Does anybody have spidey senses going off about the logarithm in the middle? 6 and 36 are part of the same power family. So if we take this to the side for a second and we rewrite it using the log loop from last class, this is 6 raised to some power equal to 36. And what power do I need to raise 6 to get 36? 2. So this entire middle term evaluates to the number 2. So when we go ahead and change all of our exponents to, what are those called? Coefficients, boom, and boom, we can also change that middle term and evaluate it since you guys know that it's equal to 2. This will become 1/3 times log base 6 of x minus 2 minus 4 log base 6 of y. We're now going to use the rules backwards. If I see that I have two logarithms that are added together, what can I do with those arguments? Multiply them. So this becomes log base 4 of 2 times 32. If we can multiply something pretty simply, we're going to do it. So what is 2 times 32? 64. So this is log base 4 of 64. Now, Spidey senses should be going off here. I only have numbers, so we check to make sure they're part of the same power family. If we go to the side and we say 4 raised to some power should be 64, can we answer that question? Yeah, 4 times 4 is? Times 4? Is 64. So 4 times 4 times 4 is 64, which means log base 4 of 64 is just 3. You always check if they're just plain numbers as both the base and the argument. If they're both numbers, we check and see if they're in the same power family. But a lot of times, there won't be numbers that are a part of the same power family, or there will be variables, and so we don't even have to do all of that mess. Let's say that we have a subtraction sign right here. If I want to condense these into one logarithm, what do I do? Divide. This is going to be log of 4x minus 3. What? Over x, close parentheses. That's it. No more simplifying needed. Really only going to simplify if it's something super quick, like multiplying coefficients. Okay, what if there are coefficients in front of the logarithms when we start? How can I change these into something else? True. You jumped ahead of me a little bit because, yes, we're going to move them up here, yeah? And because we're doing a power of 1/2, what does that mean I write instead of a 1/2 power? So this is going to be log of square root of x plus log of x minus 1 to the 4th power. If you don't see that it automatically changes to a square root, you can write a step with the 1/2 power showing, as long as by the end you change it to a square root. But we still have two logarithms. How do we condense them when there's a plus sign in between them? Multiply. So this is log of square root of x times x minus 1 to the 4th power. It's not simple to multiply all of those out, so we're going to leave it looking just like that. Okay, something very similar here. We have a 3 as a coefficient in front of at least one of the natural logarithms, so we're going to move that up to the top. This natural logarithm now is the natural logarithm of x plus 7 to the 3rd power minus the natural logarithm of x. But they're still subtracted. So what do? Divide. This becomes the natural logarithm of x plus 7 to the 3rd power divided by x. How we feeling? We're okay for now? This is about as complicated as it can get. A lot of things happening here, but let's take it piece by piece. We deal with the coefficients first. If there are any coefficients, which there's a 4, a 2, and a 1/2 power. We're going to go dump those back as exponents and move them back to be powers using that power rule. So boom, and boom, and boom. This becomes log base b of x to the 4th minus log base b of 6 squared minus log base b of y to the 1/2. If you saw that it's 1/2 and wanted to change it to a square root already, go for it. I'm going to leave this one as 1/2. But now I have 3 terms, so I need to still condense them. This is where reminding yourself that anything that's positive goes in the numerator, anything that's negative goes in the denominator will be helpful. So the only logarithm that's positive is this one, so there should only be one term in the numerator and two terms in the denominator. This would condense down to log base b of x to the fourth power over 36 times the square root of y. Where did 36 come from? 6 squared. Too easy to simplify, so we'll go ahead and evaluate that. Questions, comments, concerns? Fabulous. So we feel okay about the mad spam rules when it comes to properties of logarithms, yes? Great. We're going to want to be really good at expanding and condensing them, especially when we come to class next time, because we're going to use that skill as like step 0 of solving these sorts of equations. Now we have this last property that I didn't really explain very much. If you've taken AP Pre-Cal, we've used this formula in a different way than what we're going to use it for now, so you can kind of like put all that information on pause. The change of base formula is honestly a little bit of an outdated use. Back in my day, our calculators did not have the same sort of capabilities that they have now. And the only logarithms that this could even evaluate were regular log and natural log. We couldn't evaluate any logs with a base other than 10 or e. And in fact, before calculators, there was straight up a table, and you went and looked up table values for log base 10 and log base e. So it was really annoying for people to find the log maybe base 7 of something, because that's not something you can type in your calculator. So we developed this change of base formula that says, as long as you use like natural log or common log, you can take the log of the argument on top and the log of the base on bottom, and it would give you the value of that change of base formula. So let's prove to ourselves that this works. Here's what I want us to do down at the bottom of our paper. We're going to use both the common logarithms and natural logarithms to evaluate log base 5 of 150. So my base is 5, my argument is 150. If I use common logarithms to evaluate this, I would type in my calculator log of 140 over log of 5. If I were to use natural logarithms to evaluate this, instead of pressing the log button, I'd press the natural log button. And mathematicians found out that these values all ended up being the same. So in your calculator right now, I want you to evaluate log of 140 over log of 5. So exactly as we have it written here in the middle. You should get like approximately 3.0704. Yeah? Let's do the same thing now, except change it to a natural log. I want you to see that it doesn't matter which log base you use, that this formula will work. When you evaluate that one, what do you get? The same answer, which is really awesome. So now we have two ways to evaluate any logarithm that we can't do in our head. Because 5 and 140 are not a part of the same power family, so we couldn't even do this one in our head. That's why we get a decimal answer. But because it is now the year 2025, we have a lot more capabilities in our calculators than we did before. Does anybody know where in your calculator to find the regular log base function on here? So by using, and this is not written anywhere of your notes, so you might want to write this down, by using math and then option A that says log base, you will be able to do this without the change of base formula. If I ask you for the change of base formula, that means I'm looking for you to actually use it. And if I tell you to evaluate a logarithm without a calculator, I am looking for you to use the log loop and power families. But if I don't say, and you're just working through a problem, you can use the log base on here to evaluate. That make sense? Change of base also works, but you can also use the log base because our calculators are smarter than they were back in the day.